In this video, we'll discuss how to decode the telemetry data from our Soda CanSat using a Simulink model and a software-defined radio. Let's begin by looking at the Simulink model. Starting at the top left, we can see that a constant input called frequency is added to a constant input called bandwidth. This combined value is then provided to the RTL SDR block as the center frequency that the radio is tuned to. We also have this constant gain input, which is necessary to initiate the SDR. The output from the RTL SDR port is formatted as a stream of complex numbers, which we first channel through this bandpass filter to remove any errant readings. After this, we eliminate negative values from the signal with this absolute value block, and then we feed the signal into this FIR decimation block, which simply downsamples the signal. At this point, we have a raw signal that looks something like this, which just sort of looks like a fuzzy caterpillar if there are no devices transmitting information. In the Simulink model, we can directly pipe this raw output to the speakers of our computer using this audio writer block so that we can hear the CanSat transmissions. And additionally, this frequency analyzer block has been included so that we can double check that the signal we are receiving is well centered in the viewing window. Moving down to the lower portion of our model, we have this binary switch, which is assigned a constant threshold value. If the raw signal received by the switch is larger than the threshold, the switch returns a 1, and if the signal is below the threshold, the switch returns a 0. This provides a means to normalize or smooth the output signal within the bounds of 0 or 1. Following this smoothing operation, the signal looks more like this. Notice that the output is now either a 0 or a 1, so the fuzzy caterpillar of a signal is now gone. Now, you may have noticed these reference figures at the bottom of the model on the other side. These images show what kind of signal trains we might expect to see from the CanSat, and they will help us determine the state of the sensor on those devices. But for now, let's set aside these images, and we will come back to them shortly. But since we should generally understand what the Simulink model does, let's go ahead and fire up this network and analyze our signals. We'll begin by initiating the query radio at our base station by plugging this USB cable into both the Arduino and our computer. This query radio is just an Arduino connected to our 433 MHz transmitter and receiver. To make it look a little nicer, we have mounted everything in a project enclosure and added this LCD screen that mirrors a serial output, but all of this is not necessary. Once the device is properly configured, we can see from the Arduino serial monitor that it is periodically attempting to transmit a query message that alternates between our two CanSats. We can confirm that these transmissions are actually occurring by initiating our Simulink model as well. Listen closely, and you will hear a sequence of 3 tones. After the runtime for the model has elapsed, we can look a little closer at these signals. Let's first zoom in to one of these signal trains, and notice that each train consists of 3 sections, and that each section looks the same. This train consists of 3 repeated query messages directed to one of our CanSats. But if we zoom into the next signal train and compare the first one to the second one, you may notice that there are some significant differences. This is because the next signal train is addressed to a different CanSat. Now keep the shape of this train in the back of your head as we initiate the first CanSat in the network by removing this electrical interlock pin. And if we run the Simulink simulation again, you will notice something different shows up. We can still hear the query from the base station radio, but now you will notice that every other query is followed by a new signal train. This new signal train is the reply from our CanSat, and it consists of 4 sections that have a greater spacing between them than the query message. Now, if we refer back to those reference images on the Simulink model, we can see that the shape of the signal train we just received indicates that this is CanSat A100 under normal operations. So now we know which CanSat is talking, and we know that the sensor is below some target threshold. We can change these circumstances by simply heating up the sensor on the CanSat, which I have programmed to have a triggering threshold of around 75 degrees Fahrenheit. Once we hit this threshold, we will observe that the transmission train from the CanSat changes. Remember that we haven't changed anything in our network except for heating up this sensor, but now we can see that the CanSat is indicating that the sensor is above the threshold I previously programmed. This is also apparent if we go and look at the LCD readout of our base station or look back to that serial monitor. The sensor reading is now above 75 degrees Fahrenheit. And as cool as this is, we can make it even crazier by initiating another CanSat. Now, if we listen in with our SDR, we'll see every query is being answered, and we'll see that a new signal train has appeared. Referencing those images on the Simulink model again, we can see that this new signal train is associated with CanSat A200, and that it also indicates that the sensor is below threshold. And just as with the first CanSat, we can heat up the sensor on the second CanSat to change its signal train as well. For this demo, these signal trains have been purposely slowed down, and only 2 devices have been programmed into the network. But in theory, this architecture can be readily expanded to more devices, and the efficiency of the information transfer improved drastically. So, links to this Simulink model and the Arduino codes can be found in the description of this video. Feel free to build off of this architecture, and thanks for watching this video.